Hello. In this video, we will be discussing about the overview of the proof of the Riemann's hypothesis provided by Sir Michael Atiyah. Riemann's hypothesis remains as one of the unsolved problems in mathematics and also is one of the million-dollar questions. Now let's first get the glimpse of the zeta function, which forms the heart of the Riemann's hypothesis. Now, the following expression was given by the German mathematician Peter Gustav Dirichlet, but this expression only accepts the natural values of S. Later on, another German mathematician Bernhard Riemann extended the function so that it can accept not only the negative integers but also the complex numbers. Over here, the gamma function in the denominator is defined as the following. Let's understand the hypothesis now. It states that the zeta of S equals 0, or we can say the zeta function of S has the non-trivial zeros with real part of S being half. We get the trivial zeros for the negative even integers, but over here we are concerned about finding the non-trivial zeros. Now let's understand the critical strip and the critical line. If we consider this to be an Argand plane, where y-axis denotes the imaginary numbers and the x-axis the real ones, the portion unshaded is called the critical strip, where the real part of S lies between 0 and 1. The non-trivial zeros lie in this particular region, and the green line over here shows the real part of S equals to half, and the hypothesis states that the non-trivial zeros lie on this green line. Let's now talk about a function called the taut function, where the taut function is a weakly analytic function, so on any compact k on the complex field, T is analytic. If k is convex, T is a polynomial of some degree k of k. Here analytic means a function having a local expansion as a power series. I will put a link of a PDF stating the definition of a weakly analytic function and the other stuffs in the description below. Here K represents a closed domain, of course. Now let's define a closed rectangle as Ka satisfying the following conditions. Over here, the modulus of real part of S minus half is less than or equal to 1/4, and modulus of imaginary part of S is less than equal to A, where A is a parameter in the rectangle. Here S obviously belongs to this domain, so this gives us T, or the taut function, as a polynomial of a degree k of Ka. Now we will define some of the properties of this taut function. Now let's see the first one. Over here we can see that it is stating that the taut function of the complement of S is equal to the complement of T of S. Over here I have defined the complement function as C. The next we have T of 1 equals to 1. There is a taut function of 1 equals 1. Then the next one we have the imaginary part of the taut function of S minus half equals the taut function of the imaginary part of S minus half. The next two comes in pairs, where we have the T of root over of S equals to the root over of T of S, and the next one we have the root over of T of 1 plus S equals the T of 1 plus S over 2. Over here T means the taut function, as is quite clear. The next part is significant. The taut function maps critical strip to critical strip and critical line to the critical line. We have already discussed the concept of critical strip and the critical line. And this particular expression over here gives us a uniform constant of half. Over here I have represented it as 0.5. Moving on. The mathematician Hirzebruch expressed the stability of the taut polynomials with increase in the degree as in the form of an equation. Michael Atiyah had mentioned the name of the mathematician, the 20th century mathematician Hirzebruch, where he had already proven that the taut function gains stability as the degree increases. Over here, F and G are the power series with no constant term. Moving on. Now we will come to the overview of the proof. Now this over here comes the actual proof that was provided by Sir Michael Atiyah. Over here, the first one states that we have assumed that there exists a b, or which is a zero of the zeta function, which lies in this critical strip but is off the critical line. So clearly the existence of b will lead to a particular contradiction. And then in the next step, he has taken that a equals to b, and then in the rectangle Ka, it is clear that t is a polynomial of Ka. Now, considering a particular composite function as the following, where f of s equals to the taut function of 1 plus zeta of s plus b minus 1. Now, clearly as b is a 0 of the zeta function, the zeta of b is 0. Now, from here we get to see that f is analytic at s equals to 0 and f of 0 equals 0. Now, taking f equals to g, as already mentioned at the power series, we deduce that f of s equals to 2 times f of s. Now, identically, f of s equals to 0. Moving on, now he next deduced that t is obviously not a zero polynomial, so it is invertible in the field of meromorphic functions. Now, this particular expression that f of s equals to 0 gives us the identity that the zeta of s is also equal to 0, but this is clearly not the case. So this gives us the required contradiction and hence completes the proof. Now, in spite of Michael Atiyah's claim of having proved the Riemann's hypothesis, the proof is still considered to be unsolved. Apart from that, he had also gave a history of Van Neumann's and Hirzebruch's work, the two leading mathematicians of the 20th century, in his work. Thanks for watching. If you have enjoyed watching this video, please like and subscribe to my channel. And in case I have made any mistake anywhere, please do comment below and let me know so that I can rectify. Thank you very much.